Hi, welcome back. So in this lecture, we're going to discuss the negative binomial distribution. And this is another waiting time distribution, and it's related to our urn models with replacement. So suppose you've got an urn which has a bunch of red balls and a bunch of white balls. And well, the negative binomial distribution, well, the waiting time that's involved in here is, suppose you keep taking balls out of here, and so say you get a white, and some reds. It more or less asks, well, what's the how long do you have to wait? How many balls do you have to take until you've picked up your, say, rth red ball or rth success? Okay. Now, well, there's one sample space which you could think of taking here, which would be the total number of balls you take. So omega could be total number of balls. Which is going to, if you want to pick up r, then the total number of balls is going to be r plus 1, ... Okay, but this is a bit annoying because now our sample space is changing when we change r. So let's actually chuck this out, and let's instead take our sample space to be number of white balls before rth red ball. Okay, and well, let's actually get into figuring out what the probability distribution looks like. So let's say that P is between 0 and 1 is the proportion of red balls in our urn. Okay, well then, what's the probability of having, what's the probability of having k white balls before, like just before, k white balls before rth, yeah, maybe I'll say exactly k white balls. Exactly k white balls before rth red ball. Well, in this case, you're going to be picking r plus k minus 1 balls, k of which are white, and then you're going to pick up your k plus 1th ball as a red one. Your r plus kth ball as a red one. Okay, so well, just saying that in words, so you're going to be picking k white balls out of r minus k, so this will use binomial distribution for. Okay, so k white balls out of r plus k minus 1 red balls, and then the probability of getting a white ball is 1 minus p, so 1 minus p to the k, p to the r plus k minus 1, but then you also need your r plus kth ball to be red, which happens with probability p. Okay, so this is the distribution this is the probability we would like to assign to the event that we get k white balls, exactly k white balls before the rth red ball appears. And just rearranging this, this is r plus k minus 1, choose k, times sorry, oh yeah, this shouldn't be r plus k here. This should be just r minus 1. No, that's not working. R minus 1, right? Because we want r minus 1 red balls and k white balls. Putting this together, we get p to the r 1 minus p to the k. Okay, now this is what we would like to call the negative binomial distribution. It's also known as the Pascal distribution, but we do actually need to check that it is a distribution. So, well, we'll just give it some notation. So in the notes, we call this B, R, P here, overline, and this should go from the power set of the non-negative integers to 0, 1, and what it should have the above distribution. So the event that we need k white balls, exactly k white balls before r red balls, we want it to be this. All right, so as this stands, this gives us a function of sets. Sort of, you would extend it to a finite set. Well, you would extend to other sets in here by additivity, countable additivity. But we need to check that this adds up to 1 and that it, well, yeah, and that it's between 0 and 1. Okay, a special case of this, before we get into the general thing, a special case of this where we take r to be 1, this gives us the geometric distribution. Okay, and this would ask, well, how many white balls do we pick up? How many steps do we have to go before we pick up our first red ball? Okay, and we give it this notation, GP, K is by definition just negative binomial 1p of K, which if you put r equals 1 here, you get 1 minus 1, K choose K is 0, you get p to the r, 1 minus p to the k, so p, 1 minus p to the k. Okay, and you should be wary here that the sort of what different sources consider as success and fail, and this p and 1 minus p can change. So just note that this is the notation we're using for the course. But say Wikipedia and stuff may swap the p and the 1 minus p. All right, and this one, it's very easy to check if it's a probability distribution because this is just a geometric series. And well, the sum of this over k in z plus is just going to give you a geometric series, and you can work out that yes, this provides a probability distribution. Okay, so the next thing that we've got to do is, well, check that this thing is actually a probability distribution, and also check why we give it the name we give it. Okay, namely negative binomial distribution. Sorry, this is for general R. Okay, so for why we call it a negative binomial distribution, you may have heard of negative binomial coefficients. So these are when you've got a negative number in the top of your binomial coefficient. This is by definition minus 1 to the k r plus k minus 1, choose k. Okay, and well, great, we've given it a definition. Now, why might one want to define this negative binomial coefficient in this way? Well, recall for the binomial theorem that typically if you've got 1 plus x to the r, then this is the sum over, this is the sum over r choose n from 0 to r of, r choose n x to the r, no, x to the n, sorry. And, well, if you try this with negative r, then you actually get exactly this thing. And let's see how that works. So 1 plus x to the negative r, well, this is the same as 1 plus x inverse to the r. Okay, this is 1 on 1 minus negative x to the r, and then this thing is the sum of a geometric series, so we can just plug our geometric series in. And, well, what does that give us? It's the sum of minus x to the k equals 0 to infinity to the power of r. And, well, now you can actually just do this to the power of r, and what you get is a huge mess, but so I'll skip some steps, but what you get is pretty much what we've defined to be the negative binomial coefficients. Minus 1 to the k, r plus k minus 1, choose k, x to the k, which is k equals 0 to infinity, minus r, choose k, x to the k. So this is the reason why we would call a coefficient like this thing a negative binomial coefficient. Well, yeah, why we would call the whole part a negative binomial coefficient. And because this shows up in our binomial distribution, our negative binomial distribution, that's where the name comes from. Okay, and we can actually use this property to show that the negative binomial distribution is in fact a distribution. So let's try that now. So we want the sum over k equals 0 to infinity of negative binomial distribution of k. Okay, well, let's write this out. K equals 0 to infinity of minus r k p to the r no, I'm skipping ahead a bit. Okay, where is it? R plus k minus 1, choose k. R plus k. P to the r, 1 minus p to the k. Okay, well, we can pull out a negative 1 to the k from here. K equals 0 to infinity minus 1 to the k, r plus k minus 1, choose k. I'll just pull the p to the r out the front too. And then this is going to be p minus 1 to the k. All right. Well, this is exactly the negative binomial coefficient. So p to the r sum k equals 0 to infinity of minus r, choose k, p minus 1 to the k. And well, we've just said that this is the same as 1 on 1 minus this thing. Well, sorry, no, it's p to the r, and then this part compared to up here is 1 plus x to the negative r, where now x is this. So this is 1 plus p minus 1 to the negative r, which is p to the r, p to the negative r, which is 1. Okay, so we're done. So yes, this thing does actually define a distribution, a probability distribution on the non-negative integers with the power set as sigma algebra. So there is something that I hope people saw was dodgy, which I'll now go back to. So when we were up here, this step to this step is only valid if the absolute value of x is less than 1. Okay, so we should check that this actually held when we did our computations. And, well, yes, it turns out it does. And the reason why is that P is in 0, well, P is strictly between 0 and 1. So P minus 1 is between minus 1 and 0, excluding the boundary. So yeah, P minus 1 is less than 1. Okay, so that validates our computation here. Okay. And, well, let's just finally check where this is maximized, which would tell you sort of what is the most likely number of white balls you get before you get your rth red ball. This is actually a huge mess, but let's try do it the same way we did last time. So B of RP bar on of K divided by it, the next level down, or this is equal to, just writing it up, R plus K minus 1, choose K, P to the R, 1 minus P to the K, divided by R plus K minus 2, choose K minus 1, P to the R, 1 minus P, K minus 1. Okay, well, let's see, this is quite a mess. So I'll skip some steps, but the details are in the notes. So we find overall, after a few steps, this is R plus K minus 1 divided by K times 1 minus P. Okay, so this is larger than 1 if K is less than or equal to, clicked on something else. If K is less than or equal to R minus 1, 1 minus P on P, and less than or equal to 1 otherwise. So that means that maximized at K equals, so this should be the floor of R minus 1, 1 minus P divided by P. Okay. So, yeah, we've found that this is the most likely number of balls you have to take, how many white balls you have to take before you expect to get R red balls. All right, so that finishes this lot of sort of standard distributions. I think we've just got one more lecture on this, and then we'll move on to conditional and expectation and conditional probability. Thanks.